Hi, everybody, and welcome to this recorded Zoom interview. This is another one, but this is a special one for me. We're talking between Washington State and the Netherlands today, across the Atlantic Ocean. It's early morning here. It's late afternoon there. Professor of Geology at University of Utrecht in the Netherlands, Douwe van Hinsbergen. Douwe, what's the weather like today where you are?
It's miserable.
It is?
It's in our type of calculation, it's about 4 degrees centigrade.
Okay, all right.
It's raining, it's dark, and I'm longing for summer.
Yes, well, I think we all are about this time of the year in mid-November. Okay, well, wonderful. Viewers, can I talk directly to you just briefly, and then we'll get into it? I was watching a kind of a geology workshop, recorded Zoom talks between geologists, and Trevor Waldine. Many of you remember him. He's the Denali Fault guy, the young guy at South Dakota. Trevor gives his talk, and then it's time for geologists to put their little hands up in the Zoom windows, and they want to discuss. And Douwe shows up, and I'm like, hey, that's the Tour de France guy. What the hell? Is he interested in North America? This is wild. And you were asking about the Tintina Rocky Mountain Trench Fault, and why does it vanish as it disappears down into the lower 48? And I'm like, this is cool. And I kind of left it alone. And then I'm talking to Bob Hildebrand on the phone a couple of weeks ago, and he mentions your name, and it's like, okay, well, maybe I will reach out to this guy, Atlas of the Underworld, and on and on. So Douwe, you're like a furnace of ambition, it appears. And my first question is, are you seriously interested in North American geology, and why are you?
Yeah, I am. And I am.
Well, that's a relief. This would have been the shortest interview ever if you would have said no, I guess.
No, and I've been dabbing around it for a long time, actually.
Okay.
So I reconstruct stuff. I reconstruct how stuff moves and migrates, and I do that with plates, and I do it with mountain belts, and I do it with stuff in the mantle, and I do it with fossils, and I do it with anything that moves. So I have a global reconstruction of plates, and my last frontier is Alaska and the Canadian Cordillera.
Okay, well, I mean, I'm stunned right now and excited. Can I ask just briefly about your background? This is rare to have somebody with this many interests, this varied plate of interests. Did you have a mentor to get you thinking big like this?
I suppose I had a few.
Uh-huh.
Yeah, I've always wanted to do this.
Yeah.
I'm a geologist. I like field geology.
Yeah.
It started with reconstructing vertical motions using forams in the Pliocene of a small island in Greece, and it got out of hand.
Well, I like the big thinkers for sure, and I don't know if you have alternative views to the conventional views, and whether we touch on that today or not, it doesn't matter. Let's go ahead. I'm wanting to however you want to do this, and I'll interrupt every once in a while when I get particularly jazzed. But this is very exciting. So please, however you want to do this, Douwe.
Well, what I want to do is I'm going to do something I haven't done before, and that is 2 weeks ago, Goran Andžić and I got an idea for a paper on. I think we found finally the new view on the whole Rangelia problem that I've been looking for a while. So I want to just talk you through it and see what you think.
Okay. Wow.
So basically, just a little background.
Yes.
What I find fun is try to reconstruct plates that are no longer at the surface, but very much from a plate tectonic point of view, because the plates have the big benefit that they're simple.
Mm-hmm.
Right? There's a dozen of them. They are internally rigid and they move along plate boundaries.
Mm-hmm.
I mean, you can make the plate boundaries a bit more or a bit less complex. You can take it, the Andes, and you do this, and then you have Andes. So in the end, it's all not. I'm trying to make it not that difficult. And plates are not that difficult. What is difficult is field geology, right? So if you look in Bob Hildebrand's papers, you get maps.
Yes.
And the maps are super complex.
Yes.
And yesterday Trevor gave a talk in this online series that's there on Cordillera Tectonics.
Yes.
Yesterday there was a guy, Brandon.
Yes.
Keel,
Brandon.
Keel?
Yeah. Keel. Yes.
Gave a fantastic talk. This dude has been mapping on Kodiak Island for like years,
Mm-hmm.
and that's just Kodiak Island.
Yes.
And that's years of work.
Yes.
And if you take that entire geological map that Bob Hildebrand shows, there are dozens of people like that who have been studying and mapping for years to make that possible.
Right.
Now, the big problem is that every single one of them has clear ideas about the geological history of their part.
Okay.
If you try to integrate, let's say, a plate motion history of Rangelia versus North America, and you try to go from observations directly to plate scale, you're never going to satisfy any of them.
Oh, yes.
Right?
Yes.
For good reasons, because you know there's a lot of sweat that went into those data.
Right.
You have to satisfy them. You have to honor that.
Oh boy, this is great. This is you feel like a sibling right now. Go ahead, please continue.
The problem is that in the end, you have to make all that complexity simple, which is going to be frustrating for many. So you got to try. So what I've tried to do is to the big problem that for instance, Bob I think is running into is that you go from that super complex map into a simple solution with a few lines. Mm-hmm. And what is missing is a meso-scale, is a scale at which you can integrate all that data and justify all that data without going to the large scale, to the big picture yet.
Yes.
And that is what I've been trying to do I grew up in the Mediterranean geology, which is, and there I tried to make a reconstruction, which took a decade to get that all those pieces back together. Mm-hmm. And I developed a method there that I'm rolling out in other places that I'll talk you briefly through, to integrate the field observations on a scale that we can agree on much faster. And if we don't agree, that it's clear what we have to change. And I can share my screen to give you that.
Yeah. Look, can I ask one thing as you do that?
Sure.
So am I hearing that you tried to find the right scale in the Mediterranean, kind of the sweet spot between these different groups and different disciplines and different whatever perspectives? And did you find some traction in that community or maybe not?
Yeah. Surprisingly, that went down surprisingly well. That reconstruction is, I've run into controversy a couple of times in Tibet and in other places. And people, I mean, when you contacted me, you thought I like controversy, and I told you that I don't.
Yes.
I don't like controversy.
Yes.
Fine. Controversy is contraproductive, and controversy only means that two camps start to dig in and they won't listen to each other anymore. So I'd rather bridge and I'd rather integrate. But you have to find a way to integrate while justifying everybody's, let's say, detailed views.
It's not easy.
I think the way to do that in origins is to, accretionary orogenic belts like the Western US or like Alaska are basically bits and pieces of rock that are off-scraped from a downgoing plate. Mm-hmm. It can be entire chunks of plate where a subduction zone broke off and a new one started. You have a chunk left, or you just have this, right? You just have that.
Yeah. Oh, you did that in one of your Tour de France videos. I loved that. Yeah. I loved your sleeve going right up your arm. Perfect.
Well, that's the Franciscan,
exactly.
Right?
Yes, I loved it.
So, in the end, what you have is pieces of stratigraphy.
Yeah.
Bounded by faults.
Okay.
And the pieces of stratigraphy is where all the data come from. So the pieces of stratigraphy have a sedimentology, they have a paleontology, they have a deformation, then they can become metamorphosed, it can become intruded by magmatic rocks, you can do geochemistry on that, you can do everything on that stratigraphy and everything that happened to that stratigraphy. Mm-hmm. And there you get a relatively simple geological history. It can still be complex, but let's say on the scale of Kodiak Island, you can make that stratigraphy, or two stratigraphies, because you have an ophiolite on top of a melange. So you can take that ophiolite and you can pull it apart and work out what that stratigraphy and its history is. And I think that most of us will agree. Mm-hmm. And if you find a new age that we didn't know, then you know what to change in that particular history of that particular, let's say, tectonic slice between stratigraphies. And if you then integrate those histories, then you can come to a big picture and you have the meso-scale that I'm looking for.
And yet you're the guy talking about slabs in the lower mantle as well.
Yeah, because that's the part of the stratigraphy that it was not left behind.
Okay.
So that's the part that went down.
Yeah. Oh, yeah.
And by looking at those stratigraphies that are off-scraped, you can date when the slabs go down.
I see.
right?
I see.
You
Oh,
can put age on slabs, they can start reconstructing. Now you have a
yeah.
tie point, something
Yeah.
in the mantle that you can connect to the surface and you can
Okay.
reconstruct the mantle.
Oh, wow. I am excited. I am excited. Please, let's get started with those slides. You've got just a few, which I appreciate, but I know that there'll be plenty we can dig into just with each of your images. So looking forward to what you have. This is so great, and you're so good on camera. My God, not everybody can do this.
I've done it.
Yes, you
And by
have.
accident, somebody told me that I should do it, and I thought I can't do that, and then I did.
You did.
Okay, I
I
can do that.
I love those things.
This is my simplest version of geology.
Mm-hmm.
There are two types of stratigraphy, and that's it.
Mm-hmm.
Um, so basically, if you go to an orogenic belt,
Yeah.
then so let's say the Franciscan or Rangelia or
Sure.
Stichinia or those places,
Yep.
and we are looking at stuff that was off-scraped or left behind from a subducting plate and accreted to another plate.
Yep.
Then that stratigraphy can either be part of. Do you see a pointer?
I do. It's small, but I can see it. Yes.
Let me see.
Oh, look at this.
Here.
Oh boy.
Pointer.
Oh boy. Here we go. Yeah.
Right?
Great. Thank you.
Red and green. That doesn't work. Anyway. So either that stuff that is off-scraped came from an oceanic lithosphere or from a continental.
Right.
Right?
Yes.
So typically downgoing plates are oceanic and then something continental comes in and then we call it collision. I don't like collision as a term. Okay.
Okay.
Right?
Yeah.
Now, if you have an oceanic plate that goes down, this is a concept that was developed by a guy called Izuzaki, a Japanese guy in 1990, which I think is a brilliant paper if you want to read one.
Thank
It's
you.
really fun. That paper is a rant. It's an angry rant against Europeans
Oh wow.
who came to Japan and who treated Japan as the Alps. And he says, this is not the bloody Alps. Look at it.
I love that.
It's a great paper. You should read it.
I will.
Technical physics paper.
Okay.
Anyway, he came with the concept of ocean plate stratigraphy, and all of Japan is built up like this.
Mm-hmm.
So you find a thrust slice, and that thrust slice consists from top to bottom of trench fill deposits.
Mm-hmm.
And below the trench fill, you will find hemipelagic and radiolarian cherts.
Okay.
And that's deposited on some ocean floor. And if you have a chemistry of morb, you know that that ocean floor formed at a ridge. And otherwise, you have some seamount and you have otherwise some seamount. Okay?
Mm-hmm. Okay, good.
And you can off-scrape that and you can stack that on top of each other.
Mm-hmm.
That stratigraphy tells you geological history. It tells you that this particular stratigraphy came from an oceanic lithosphere that formed at a mid-ocean ridge.
Yes.
If you date the oldest charts, or you can date the morb, you know what the age of that when that ocean floor formed. And if you date the age of the trench fill, you know when that ocean floor entered the trench.
Okay.
Okay, and the time difference between that tells you the age of the ocean floor at the moment of subduction.
I like that. Never thought of it that way. Thank you.
Well, what Izuzaki showed beautifully in Japan is that you see, he calls it OPS, ocean plate stratigraphy, that the ocean floor that entered the Japan trench first became younger and younger and younger and younger until 50 million years, when you have morb intruding trench fill, meaning that the ridge entered the trench, then it becomes older and older again. So you see the Izanagi Pacific Ridge approaching, arriving, subducting, and then the older and older Pacific coming.
At 50.
At 50.
Okay.
So with this, you can reconstruct, and I'll do that for California in a minute.
Oh, wow.
With this, you can reconstruct the ocean floor age and perhaps ridges in that ocean floor that are approaching and entering trenches.
Mm-hmm.
And the good thing of that is that mid-ocean ridge or oceanic plates are super simple creatures.
Mm-hmm.
They're very and I'm sure there are people angry now, but in principle, they're huge chunks of rigid infrastructure with a very gradual age progression.
Yes.
There may be a transformer, that's about it.
Absolutely.
So with a few of these pieces of information, you can do a lot.
Feeling very comfortable so far. Good.
Yeah. Now, you can do the same thing for continents. We did that a couple of years ago. But continents from top to bottom have something similar. Typically, what enters a trench is a continental margin.
Mm-hmm.
And a continental margin that has entered the trench from top to bottom has a Farallon basin deposit, which may or may not be deep marine, can be a fleece, morass, or whatever.
Okay.
Then you go to hemipelagic clays or marls. You have a passive margin sequence, typically carbonates, deep or shallow marine.
Mm-hmm.
Then you have, again, hemipelagics. Then you have synrift deposits, perhaps with mafic volcanics. And then you get basement of an earlier orogenic phase.
Mm-hmm.
Right? And you can make that, of course, a bit more complex because sea level changes may mess around here a bit with your stratigraphy, or you have, or Wrengelia, you have a large igneous province playing around. So you can make it a bit more complex, but overall, this is the stratigraphy that you find in every continental nap. In the Himalaya, in Greece, in Turkey, in Iran, it always looks pretty much like this.
Okay.
And from this, you can see the same thing. The moment that this continental margin arrived in the trench, you can get the passive margin history. You know when this continent broke off from some other continent. Often these are microcontinents or so. You can see when they broke off. And then in the basement below, you can get the information. You know, what is a continent itself? A continent is just either accreted crap or a craton.
Yeah, yeah.
Right?
Yeah.
So, and the accreted crap is this again.
Yeah, yeah.
So with this you can integrate now all of that information that we get from the field. You can make this stuff once a sequence like this. So you can get all the information on paleolatitudes, for instance, that is taken from these rocks. Your ages, your history, the ages of breakup, the ages of formation, the ages of drift.
Yeah.
Anything you can get from this. As soon as a nap like this is buried in a trench, this may metamorphose, this may intrude, but on this scale, I think it is relatively easy for geologists of different specialty, let's say, to integrate their story into something that we agree on.
Very good. So this is what you devised years ago. This is not the 2-week-old idea. This is
the basis.
Yes. Good.
Okay. So that's the idea.
Love it.
So what we'll do now is Joe Wakabayashi, that I worked with and that you know, no doubt, has worked for decades in California in the Franciscan.
Yes.
Here. On every aspect of it. And he published a paper in just a couple of months ago with a figure that I think he made this figure already 10 years ago. He keeps updating it.
Okay.
What you see here is essentially what I would call an orogenic architecture diagram. So every column here is a piece of ocean plate stratigraphy that is stacked on the next that he found. And it's not just John, of course, who did all this work. Dimitri did a lot, and there's lots of people who had lots of stuff to do here.
Probably going back to Eldridge Moores, I'm guessing.
Oh yeah, and so John is a student of Eldridge,
yes.
And I'm sure that before that time there were people.
Yes.
So in the Franciscan, the Franciscan is a sleeve, right, of a whole bunch of that ocean plate, just stuff off-scraped from an ocean. Most of the ocean is gone. But here and there we have these pieces left. And this is what John showed. And what you see beautifully is a Farallon propagating sequence of thrust slices that accreted. Well, the subduction zone started something like 180 million years ago, and the ophiolites formed about in the upper plate about around 170. And then we get accretion. Now, what you see in these, so every column here has a mafic basement from the ocean floor.
Okay.
Then then a bunch of radiolarian cherts, and then in blue some Farallon basin deposit. Okay. Now he indicated here what the geochemical composition is of that mafic basement. If it's more, it came from a mid-ocean ridge.
Yes.
If it has a question mark, he doesn't know what it is. If it's an OIB, it's an ocean island basalt, so it's a seamount. It's some plume-related seamount, which does not tell us the age of the ocean floor, but only a minimum age.
Right.
Now, 3 columns are of importance. Number 2 has too much uncertainty, but number 3 here has a mid-ocean ridge basalt that is 140 million years old at the basis, and a Farallon basin deposits that's 120.
Okay.
So here, ocean floor of 20 million years old at the time of subduction entered the trench. Okay?
Mm-hmm.
Then we have pile number 5. There we see at, I believe this is 110 million years, we have mid-ocean ridge basalt coming in that is 170 million years old. So it's getting older.
Yes.
And then here at pile 8, we have a mid-ocean ridge basalt that is 190 million years old that arrived in the trench 100 million years ago.
Yeah.
Right?
Weird.
No?
Not weird.
No, it's just what it is.
That's what you'd expect?
I don't expect anything. It just it is.
Okay.
Let's have no expectation. Okay.
All right.
Let's just have zero expectation.
Okay.
So why do you think it's weird?
Well, I'm trying to think of what I would expect if we have just ongoing steady subduction of a Farallon plate, which is the classic traditional view of this 50 years ago at least. And I would expect an orderly scene where we're just continuing to scrape, and whatever the pattern would be, I'd expect to just see repetitive pattern throughout the whole, 180 million years of ongoing subduction of a steady plate. And
if that plate, if that lithosphere would have formed at the Izanagi Farallon Ridge,
okay,
or at the Pacific Farallon Ridge,
yeah,
then it should get younger
Yes.
Yeah.
Yes.
Then because then the oldest subducts first, and then you get younger and younger.
Correct. That's right. That if we are expecting something, Douwe, that's what I would expect, and I'm not sure I'm saying that.
I'm very sure you're not. So the conclusion from this simple observation is that what is subducting here is ocean floor that did not form at the Izanagi Farallon Ridge.
Hello. Okay.
Full stop.
Mm-hmm.
And Johnny Wu, I think, and John Wakabayashi have already shown this at last year's A conference. And Johnny just had a few papers out that may contain this, but as I said, this is quite fresh. So we just looked at this 2 weeks ago.
Okay. Okay.
But I think that they already drew this conclusion. Okay, then the next step is I'm doing this with Goran Andžić, and Goran is one of the few people alive who can recognize radiolarians.
Mm-hmm.
Very useful. And he has redated a few of these things. And importantly, he has redated this number 10.
Okay.
And the number 11. The flèches here, so the Farallon basin deposits here, of these ocean island basalt sequences, entered the trench between 93 and 81 million years. So these are too young, these estimates. Yeah. So after 100 million years, we have this 190 MA morb. We get accretion of 2 blocks. We don't know what the age of the ocean floor is because it's just some Hawaii island, Hawaii-like. But there's accretion until 80. Then there's a gap, and then the next one accretes at 50. Right? So between 80 and 50, there's a gap in accretion.
Okay. 80 and 50. Okay.
Just remember that.
Yeah.
Okay. Now, so what you can do now is I'm going to show now a few maps that integrate a few things that I want to explain, and it's all on there already.
Okay.
So I'm just going to point out at the effect that you might see. Oh, sorry about that.
No problem.
Sorry, ik moet. Oeh.
You okay?
No, I tried to get rid of somebody who's calling me.
Oh.
Sorry about that one.
Pick up your kid right now. Come on, quit.
No. I was so friendly yesterday to There you go.
Okay.
I was so ready yesterday to give somebody a donation for Gaza, but now they have to call to see
Oh,
if I.
sure. Of course. Yes. Okay. All right. Well,
Okay. Okay, back to this.
yes. So you have a perspective. You have a bag of tricks. You're not just a California geologist. You're I don't know how you got going with John and others who've been working in the Franciscan. Maybe that's an interesting question. Did they invite you to help with some of this breaking news, or how did you come to play with this game here in Western California?
I was working years ago. I was working.
Can you stop your share for a sec?
Yeah, sure.
Just love to see a little bit more here. Yeah. So what is the backstory here? I think it might be interesting to see how this fits.
Well, a few years ago, I was doing paleomagnetism, which I did a lot in the Tethyan region.
You do everything. Holy cow. Okay.
Well, I do tectonics, so you know, that integrates stuff.
Okay, good.
So I like doing paleomag because it's the only constraint we have, quantitative constraint of paleogeography.
Okay.
And with paleomagnetism, I was reconstructing. With paleomagnetism, you can do something cool with ophiolites. Ophiolites are upper oceanic plates, right?
Yeah.
And suprasubduction zone ophiolites, like the ones in California, form in the early stages of subduction. When slabs collapse, and you can start to reconstruct from that what the direction of spreading was in the ophiolites if you do paleomagnetism or sheeted dike sections.
That's a new thought. Okay. Yeah.
So you can reconstruct. You have to do a few tricks, but you can reconstruct what the orientation of sheeted dikes are in ophiolites. And sheeted dikes form if you have two, where two plates spread apart, magma goes in, and it makes, at the mid-ocean ridge, it makes a series of dikes.
Uh-huh.
So if you understand the orientation of the dike and you can reconstruct it to the position that it formed in, you know the orientation of the ridge at which it formed. And if you know the orientation of the ridge, you know the orientation of the spreading.
Okay.
And we use that to reconstruct the relative plate motions in the neotethys during subduction initiation. And I wanted to do that in California. So we did that in the Diablo ophiolite. And I contacted John then to see if, because he knows that thing.
Okay.
That's where we did a collaboration. And I had a master's student who published a nice paper about it, Jamil Arkula. What it shows is that the Californian ophiolites formed by north-south spreading, so parallel to the trench.
Parallel to the trench, right.
And what we showed is that the age progressions that you see, or the different ages that you see in the ophiolites across California, that you can reconcile them with one spreading center that is offset with a few transforms and an 8 centimeter per year spreading rate.
That's new. I haven't heard that before.
We published it in Earth Science Reviews in 23.
Okay.
What the cool thing is that you basically you can show that all of those small little blips of ophiolite that you see in California are the remains of one coherent plate.
Now, where are we? Is this older than 80?
Yeah, this is 170, 170, 160. It's the early stages of spreading.
Okay, so I'm remembering the 80 to 50, but we're not there. You're
not there yet.
Yeah, okay.
Well, you distracted the story because you wanted to know about John.
Yeah, that's right.
This is how
I did. That's right. No, this is good. No, the backstory I think is helpful. And yeah, I know we're heading to the 80 to 50 and possibly bringing in another region. I think that's where we're headed, but I'm not quite sure. So yeah, I mean, there's all sorts of lessons here, but I don't want to distract us here. Let's go back and continue the story. And this ultimately helps us. I don't know. I'm trying to keep on task here, but my mind is racing with Baja BC and all sorts of stuff, that all the implications of this.
I'm not going to tell you the implications. You can do that yourself, because as soon as I give implications, everybody will disagree.
Yeah, sure.
So you can do that yourself. But let's just think about one thing.
Yeah.
We now saw what the hard field work of John and his colleagues in California has shown is that the ocean floor that is subducting between 140 and about 100 million years,
Yeah.
is ocean floor that did not form at the ridge between Izanagi and Farallon, but between Farallon or something else entirely. So you need a spreading ridge between Farallon and North America.
Yeah.
At least a spreading ridge, and maybe more. Okay?
So even the classic debate about eastward versus westward subduction along the California margin, during this time window, it's a moot point because we've got the spreading ridge perpendicular to the trench?
Well, the east or west dipping subduction has to do with the relationship between, I think, the Klamath Mountains and the Sierra Nevada arc and North America. So that's east of the Franciscan, right?
Yeah, yeah.
So whatever it was, whether it was one or both, actually, if you had westward dipping subduction in Jurassic time, let's say, below a Klamath, Blue Mountain, Sierra Nevada arc, then you would have a way to make a ridge between Farallon and North America, because you can roll that back and make that ridge that we see the results of, right?
Wow, yeah. So
that could work. But whatever the discussion on west or east, that is east of us.
Yeah. Okay. I got you. The fact that you're that deep into this stuff and you know about the Blue Mountains, which is in my neighborhood, I mean, that's a thrill just alone. But anyway, very impressed for many things here. Yeah.
I think that's a very important piece of infrastructure. I'll get back to that.
Yeah. Okay.
I don't know so much about it, but I think that is a key point.
Good.
Anyway.
Good.
So that's one thing. This is what we can learn there. What we don't know yet now is whether we are looking at Farallon or at a different plate.
Right.
Because it's still possible that we're looking at Farallon, but that Farallon had a ridge in the west and a ridge in the east, and that we now look at the part that formed at the ridge in the east.
Okay.
But if we go farther south, we get answer to that in the Caribbean.
Because I'll bet your Atlas of the Underworld is going to help us here.
Actually, it won't.
It won't?
Yeah, deliberately not. There's been a big discussion. So one thing that was added to the debate 15 years ago or so is Karen Ziegler's point of view, right? What she called tomotectonics. Yeah. And at the same time, we were working on this atlas, and we had a paper with Douwe van Hinsbergen in 2012, in which we did that without calling it that.
Right.
What Karen does is, she pointed out that there are these two parallel bands of slabs.
Yes.
Below the western US and the eastern Pacific. And that would call for two simultaneous subduction zones. But if you want to use that to make a reconstruction, it means that you need to understand how the mantle works in order to make a plate reconstruction. Right? You need to know how fast slabs sink and whether they move horizontally, and you need to assume all of that.
Okay.
But I'm making plate reconstruction to figure out how the mantle works, not the other way around. So I do not use tomography to steer the reconstruction. I use the reconstruction to interpret the tomography.
I see. Interesting.
Right? Which doesn't mean that I disagree with with the approach of Karen, the approach of Johnny Wu.
Right.
It's just that I want to learn about the mantle, so I use the plates and not the other way around.
Yeah. Okay. This is fun.
So let's go to the Caribbean.
Good. Why not?
Let me share my screen again.
Love it. I'm gonna milk this as long as we can talk. You're gonna cut us off when you got to go pick up the kid at daycare or whatever. Okay, that's our deal.
We have a trumpet lesson coming up, but I think
okay. Well, So you keep an eye on the clock.
Otherwise, we'll continue later.
Okay.
Hey, here's a slice. I forgot to put the ages here. Here's a slice at 80 million years ago.
80.
Forget anything here.
Okay.
You see stuff that you're familiar with. Kula in some form that we don't entirely know what it looked like, but we know it. We know it here, spreading away from the Pacific. Farallon, which is all subducted, so we made this up based on Pacific anomalies.
Yes.
And here's the Caribbean.
Good.
Now the Caribbean, and this is an important point, the Caribbean plate is now sandwiched between the Americas, right? It's now located here.
Yes.
We can quite confidently reconstruct it back to this position, and I'm not going to go into all the details, but there's something important in the Caribbean. There are two subduction zones in the Caribbean.
Mm-hmm.
The Caribbean is in an overriding plate position relative to both.
Okay.
We have one here in the west, the Panama-Costa Rica subduction zone, right?
Mm-hmm.
That subduction zone is about 100 million years old.
Okay.
And we have one here now in the east, but particularly in the north, below Cuba. And that one started 140 million years ago. And these ages are not controversial.
Okay.
Right? There's arc on Cuba that started at 130. There's all sorts of blue schists and eclogites in Cuba that have 125, 130 MA ages, and it's super subduction zone crust. So people agree that this is let's say early Cretaceous, about 140.
Good.
If this subduction zone at 100 million years formed 100 million years ago, then before that time, there was a subduction zone.
Okay.
And there was also not a ridge. We know that because there's very old rock in the overriding plate, old oceanic floor. So before 100 million years ago, Caribbean and Farallon were the same plate. Right?
That's cool.
Then when the Caribbean starts to hit Nicaragua and South America, perhaps added by a large igneous province here, 100 million years ago, there starts to be a subduction zone in between. We get a separate history.
Jesus, that's cool.
Okay, now the important point is, if Caribbean and Farallon are the same plate before 100 million years ago,
yes,
then I can reconstruct the Caribbean with Farallon back into the Pacific realm.
Right.
Right? And if we do that, this is 100 million years ago when it starts hitting.
Okay.
Now we go here, then that subduction zone of Cuba is located there.
There we go.
Now, this subduction zone is the plate boundary of Farallon, which means that north of Cuba was a plate that cannot be Farallon.
Yeah,
right?
Right.
Which is the plate that has that ocean plate stratigraphy that is subducted below California.
You son of a bitch. Look at that.
So that plate that is subducted below California is not Farallon, because otherwise there's no subduction zone in Cuba.
Mm-hmm.
It had a ridge in the east and an unknown plate boundary in the west. I draw here a trench, but we can also make it a transform. Right? As long as but this plate here must move south relative to Caribbean. South-ish, as long as there's convergence. Okay?
And the 3, the 5, and the 8 are those little portions of the little strat columns that you had in the previous map. Okay.
Right.
Okay.
Okay, so what we have here is a ridge that was active until 140. That ridge must have subducted below the Franciscan later than 140, 130 or so. Whether it was active at that time, that we don't know. I don't know whether maybe there's something in the arc here that indicates that there was ridge subduction. Don't know whether people have speculated about it. But it may have been active, may not have been active.
Okay.
At that time. But at 140 it was active because we see that in the ocean plate stratigraphy. And with that ridge, you get this age progression. And then the question is, what was this plate boundary?
Yeah.
And where did it go? Well, if we want to know where it went, I have to look. And we're working on Alaska to see where it goes. We'll figure it out because, plate boundaries are not that difficult. That's the pleasant of it. As I said, geology is difficult, but plate boundaries are not.
Okay, that's the first time I've heard anybody say that. And you are thinking about doing some work with Alaska implications?
Yeah, we're working. We're digging in on it.
Cool.
So Johnny Wu called this a bridge river plate.
Okay.
He was playing with this. He came from the point of view from tomography, which I do not. Yes. But so I'm using that name that he introduced. Now, this plate boundary here could have been a transform, in which the bridge river plate is moving dextrally relative to Farallon, then it would converge with Cuba, and we satisfy the constraints.
Okay.
You have a ridge here, transform there, trench here. In that case, this transform would arrive at that trench when the Caribbean margin here hits Nicaragua. Right? So that's here. Then here, this blue line So this is that subduction zone of the Caribbean, and connected to that point, you would have the transform that is subducting, and after that, you just have subduction of Farallon.
Okay.
If you do that, it means that there was never, since 140 million years ago, there was never a subduction zone west of the Franciscan.
Never a subduction zone west of the Franciscan. Okay.
Yeah?
I'm not sure I see that. West.
Okay.
Try that again.
If this is a transform,
yes,
then east of that transform, I have that ridge plate
yeah.
moving south.
Yes, got it.
And west of it, I just have Farallon and spreading away from the Pacific.
Yeah, got it. Okay.
So it could have been just to satisfy this set of observations,
right,
to do with the transform and make a scenario in which there was never a subduction zone west of the Franciscan in the ocean. The alternative is that it was a subduction zone.
Okay.
If there was a subduction zone, it can be west dipping or east dipping. West dipping doesn't make a lot of sense because we got to make a spreading ridge here with a west dipping subduction zone and an east dipping one. I cannot think of a way, maybe this goes into too much detail right now, but I cannot think of a way to initiate that subduction zone if it is surrounded, if it on both sides has this ridges. If it is an east dipping subduction zone, it could have been old. It could have existed long before this ridge existed because it's in a back arc position, this ridge. So I'm playing with an east dipping subduction zone.
Okay.
If you have an east dipping subduction zone here in the connecting to Cuba, you have opposite subduction polarities, so you need a transform in between that lengthens a stepfold.
Okay.
Yeah, there's a system today between Vanuatu and Tonga that has that.
Okay.
Right? So this point will run along that line to the next position here. So now we have the Caribbean subduction zone here, the intraoceanic subduction zone there.
Yes.
We don't exactly know where. We can play a bit with that position.
Okay.
But what it means is that because of the opposite polarity, you need to keep convergence across those two plates.
Okay.
It means that this subduction zone has to arrive at the North American margin long after the Caribbean plate does.
Okay.
We don't know how much after, but after.
Yeah.
Now, when is our opportunity when that could hit? It must be after 93 to 81, the youngest accretion. Basically, it can happen between 80 and 50 when we have no accretion in the Franciscan margin. Between 80 and 50, any record of that subduction zone could arrive at the margin or close to that margin between 80 and 50 and move north with Kula. You can get rid of it and only have one Franciscan record. So those are your two options. The conclusions are there must be a separate plate between Farallon and North America. This one?
Yeah.
It either had a transform and there was never a subduction zone between Franciscan and Farallon, or it had a subduction zone and that subduction zone could have, and that arc associated with it, could have arrived at the trench between 80 and 50 and moved north.
So how much of this is the 2-week-old idea?
This is the 2-week-old.
This is it. Okay. But Johnny had this plate for a while, but you're trying to match it with the Franciscan.
No, I didn't know he had the plate until I made this and then figured out he made a plate. So I used the name.
Okay. Good. I mean, thank you for this. Is there anything more slide-wise, or can we finish with a little bit back and forth with just the two of us?
We can finish with the two of us.
Yeah. It's exciting, number one, to be part of this. Suddenly you're dark. I don't know if you've turned the lights off and you got one foot out the door already. I don't know. Did they cut?
No, I don't.
You paid the power bill?
The weather.
Okay.
It's getting dark here.
Okay. All right. Well, I should definitely close up then with you. It's exciting to be part of this discussion. So thank you for that. I'm going to use a bunch of this over the course of the winter when I'm ready for it. So some of this is too early for me, and I can't quite wrap my head around it. Of course, we're trying to reconstruct a bunch of stuff. That goes without saying if we're talking about Alaska. But this month, and this part of this series I'm doing with Alaska, we're trying to establish things down here and then bringing them north to Alaska. Maybe that's a final thing we could get from you. What specifically in Alaska intrigues you or potentially has a connection to the topic that we had today?
I think what you just looked at is the history of Rangelia.
Okay.
It's Rangelia between 140 million years ago was that arc on the Bridge River Plate.
I see.
And the Bridge River Plate then is a back arc behind Rangelia and behind the Klamath Mountains and Sharon.
Okay.
And actually, if you then restore the Klamath Sierra Nevada arc and Rangelia and you close that back arc basin, they become one and the same thing.
Okay. This is great. This is really fun.
Which is something that George Garrels and Jason Salibi said in 1987. I saw yesterday. But
okay. Well,
so you rift one off, you open the back arc basin, one becomes California, the other one goes north, and is now Vancouver Island.
Very,
is my guess.
Very fun. Very fun. Hey, I'm going to stop the recording. We can talk for another second before we go to the trumpet lesson. But thank you so much for your time, Douwe. Really loved this discussion. Thank you for your time.
Think it through, and we'll chat again.
I love it. Thanks.